Let me pull up the assignment, and I'm going to go ahead and talk about the basics for doing encryption. Okay, so okay, and it's on the TV up there. All right, so. So encryption algorithms are they are an interesting thing to study, but more importantly, they are extremely, they've got an extremely long history. First well-documented encryption algorithm dates back to around the early, 3rd century or something like that. Or not 3rd century, 1st century. Back in the days of Rome, which we call, and it goes back to something called the Caesarian cipher, named after Julius Caesar, of all people. And it works fairly well, especially it did back in the day when we, really what we cared about was, keeping basic messages hidden, and most of the people in the world could not read. So, kind of useful there. So, anyway, the idea here was that you're sending out orders to your generals, right? The most common one is this. Attack at dawn is basically the hello world of cryptography. And you want to keep that concealed. You want to send that message, and you want to send it securely to somebody else, and then when that other person gets it, he's going to be able to decrypt it. So encrypt it is to turn this information into what will look like gibberish, but it's not gibberish. It will look like gibberish to somebody else. And then if they have the appropriate key, you'll be able to unlock the data. Now here the key is used for both locking and unlocking. Some encryption algorithms, they use different keys for locking and unlocking. But here, the encryption for Caesar cipher, again, this was the height of 1st century security. So it was essentially, hey, we'll take our letters, and what we'll do is that we'll move them 3 ahead. So attack at dawn would become D, right? So you'd have D is 3 letters ahead of A. So T, S, T, Q, R, S, T, U, V, W, right? W, W. D, and then what's after C, E, F, G, and K, L, M, N. So that would be that. And then you'd have DW, and then D would be EFG. Wait, sorry. C was DEF. G, A, sorry, D, Z, and then N. N, Q. And so our general would, so I would send a message to our general, and he would get this message, attack at dawn, right? Okay, so he'd get attack at dawn. And he'd actually get, I don't know how to pronounce it. But anyway, he'd get that message, and what he would do then is that he knows that the key is rotate everything 3. So I rotated everything forward 3, so he's going to rotate everything backwards 3. Right? So he would just simply subtract 3, go backwards 3, and he'd get A from D, T from the W's, D from the A, and so on and so forth. Now, and so he'd be able to get attack at dawn. Okay. However, this whole idea of doing the encryption like this isn't particularly secure, right? Because there's only, if you're just using a Caesarean cipher, there's only like 3 different ways you can, there's only like 3 different, sorry, there's 26 different possible rotations you can do, right? There's other ciphers as well. There's substitution cipher. I mean, you can, this is what's a substitution cipher, where we substitute every letter with a different letter. There's also transposition, where we basically could move letters around, but we'll just focus on basically changing the letters. Okay, so that's kind of the issue there. Moving forward to the 1900s, just to mention it, we've discovered there is one and only one completely secure encryption method, and that's called a one-time pad. And that's where we have basically 2 pads that are identical. I have one, you have one, made of completely random numbers. And what we do is that each letter, I take a look at that number, and I move it forward that much if I want to send it. So like I take the first letter, and if that's 1, I would move this forward 1. T, if it and T, if I had 13 was the next letter, I would move that forward 13. And then but it would be always completely random. But you'd have the same random numbers on your pad. And the reason it's called a one-time pad is that once a number was used, we would never use that number again. We would never use that, we'd never use the first number again, second number, and third number. I mean, there could be another 1 in there, but the idea is that basically that once we've used a number, one of these completely random numbers, like if we sent a message that was 13 letters long, we'd start on the 14th letter next time we communicated, right? And the idea is that basically that because these numbers are completely random and they're as long as our message, there's no information we can grab out of it. And that's kind of the way that encryption is broken. By finding by basically using a lot of fingerprinting is kind of the way that encryption was broken. Now it's a bit more tricky when you learn about RSA and that kind of stuff. But the way that basically encryption would be broken like this is just simply look for the most common letter, assume it's E, and work from there. Okay. So the Caesar cipher, was secure until people realized what the technique. After that, we had the Vignere cipher, which what we would do would be we would use a word to encrypt everything. So let's go ahead. So in most ciphers, we simply do we split everything up into 5 letter groups. And here for what we would do is that for this cipher, we would take A and move it forward S number of letters. So if S is, I don't know what letter of the alphabet it is, but say it's like the 16th. I don't think it is, but say it was the 16th. We'd move A forward 16 letters. And then this T would be moved forward N letters. And this one would be moved forward 1 letter. Right? And so on and so forth. We'd encrypt each letter individually. And there would be kind of a repeating pattern. And so this was the height of basically security during World War I and the Civil War. This was very time-consuming to solve. And the point of encryption is not to keep your information necessarily hidden forever, just to keep it hidden for a certain amount of time. And often if it's orders, then being secure for a day or so was perfectly fine. Modern encryption systems rely off of however, you have to know the keyword. You have to know the keyword to write the message in the first place. Modern encryption systems, however, they rely off of using computers and prime numbers and very interesting relationships between them. So, but the process remains the same. I went ahead and wrote these, and I'll rewrite them in class today because this is an essential part of what you'll need. But this is the way encryption works when we do it via coding, which is that if we want to encrypt a character, we actually have to do some weird arithmetic with it. And I'll explain that in more detail later. But the idea here is that basically we can write something, given a character, and I want to move it forward given the character A, and I want to move it forward 3 characters, right? This will give me D. Right, now the important thing to also remember here is that basically if I wanted to move a letter like Y forward 3 spaces, Y is at the end of the alphabet, so we're just going to wrap around in that case. So Y moving forward 3 would be B. Okay. So anyway, that brings us to our current topic, which is Cryptonomicon. So Cryptonomicon is a book, a real book that's been written by a real author. His name is Neal Stephenson, and Stephenson is known for some books. He's written a couple. I think the best one of his I've read was Reamd, which is about cryptocurrency, ransomware viruses, the Russian mafia, Chinese gold bots, a lot about Russian firearms. He's very prolific. It's very, very good, and it reads like an action novel, unlike some of his other stuff. But part of his that book doesn't suffer from one of his problems, which is that that most of his novels basically are like his editors just finally just come in and say, no, stop writing. So he's very good at writing, not so good at finishing. Like Seven Eves, another good novel. It's like 2/3 of the novel is like one complete story, and then like 1/3, the last bottom third, takes place 2,000 years later and is like an incomplete sequel. It's really weird sometimes, but he's very good. So he wrote something called Cryptonomicon years ago, and what he did is that he wanted 2 of his characters to communicate covertly, but he didn't want them to use electronics, and he wanted to have basically a secure means of communication between these characters that wouldn't be necessarily easy to see. And he asked Bruce Schneider, a real life security expert, to develop an algorithm based off of deck of playing cards. Because there's nothing suspicious about you carrying around a deck of playing cards, right? And, whereas basically if you had a one-time pad, that's super suspicious. So the idea here is that you don't use a deck of playing cards as an actual deck of playing cards. But instead what you do is, and again, you'll want to grab half the cards. You'll want to grab one of the red suits, one of the black suits, and both the jokers. Okay? And I'll have them in a particular order. What I'm going to do for simplicity's sake is that I'm going to have the red cards all on top in order, so 2 through ace in order, and then 2 through ace for the black cards on below that. And I'll put my colored, and I'm going to put my colored joker between the 8 and the 9. The red 8 and the 9, and I'll put my black and white joker between the black 6 and 7. Now the reason I did this is because that the way this works is that you memorize. We're going to be doing it on the half deck, but the way the algorithm really worked was that you'd use a full deck, but half deck for simplicity's sake. The way the algorithm works is that we have a deck of cards that we've maybe memorized the order of. We have some predetermined starting configuration for a deck that we've memorized or figured out. Okay, maybe you're just counting up by 3, so you start with the 2, then you go up to the 5, then you go up to the 8, right? But what we do is that we assign each of these cards a value. Oh, right, one more thing. Put your aces first. Aces should be counted as 1s for simplicity's sake, by the way. I know, that's weird. But what we're going to do is that we're going to give each of these cards a value. So the red ace 1, the red 2 should be 2, red 3 is 3, So the ace of heart, sorry, the 4 of hearts should be 4, 5 of hearts should be 5, 6 of hearts should be 6, 7 of hearts should be 7, and so on and so forth. And then when you get to your face card, so your jack of hearts will be, let me go ahead and, can everybody see me on the board now? On the screen up there? No. Okay, right. I forgot about that. Give me 1 second. Preview, full screen projector. There. Can you see me now? Yes. All right. So, the jack of hearts should be 11, 12, 13. And then we start wrapping around, and then we basically continue on with the black card. So your ace of spades would be a 14, or ace of clubs if you're using clubs instead. Then the 2 would be 15. So basically it would be 13 plus the value of the card. Okay? With the colored joker, and now each of the jokers, they're distinct. So I'll call this one, the colored one, Joker 1, or Joker A, and he'll have a value of 27, and the black and white joker will have a value of 28. Now I put mine, if you want to follow along, between the 8 and the 9. And I put my my black and white joker between the 6 and the 7. And the idea here is that we've memorized this configuration. That way if the deck gets rifled through, then I can just immediately return it to the state. And the idea here is that I will use this deck to generate random keys for me, right? I'll use this deck to generate random keys, or at least something that approaches statistically random keys. So, whoops, closed, full screen. So, the way this works is it's a 5-step algorithm to generate the key for encrypting a single character, right? What we do is that we go through these 5 steps. I'll just use my other deck here to just not even demonstrate, but just like show. I'll generate all the steps, and then aha, it's an 8. It's the black 8. So I'm going to move forward. So my key is going to be 8 plus 13. So it will be. So I'm going to take my first letter and modulate it, and rotate it by 13 plus 8, which is 21. Yes, 21. Okay, and then I'll do my algorithm again, right? And then I'll pull out the next card, and it's, aha, it's red 5. So so I'm going to take the next character and move it forward 5 characters. Make sense, everybody? And then I'm going to keep doing that for as many letters as I have for my message. Okay? And part of the brilliance of this is that a deck of cards is 52 cards plus the 2 jokers. Okay? And how many letters is the English alphabet? It's 26. The same size, which is kind of convenient. So, all right. So how does this work? So the first thing we need to so how does this algorithm work in practice? The first thing we need to do is find the A joker. So that means that basically we find the first joker. Let's go ahead and I'm going to, give me 1 second. Yeah. You don't want to necessarily cut the card, shuffle the card, unless you want to actually be starting from a really random configuration. Give me 1 second. Ah, that looks terrible. What did I do? That looks terrible. I'm sorry. Oh, there I am. And now, let's see if I go up. Is my arrow there? Let me see my arrow. I know the height of... Oh, there I am. Okay, awesome. That is weird. Why are you like that? First off, you should be over there. Next, apply. Okay, next, let's go ahead and do, yeah, we'll keep these changes. Next, Okay, next my primary display should be my built-in display. Thank you very much. Keep changes. Okay, I would like this to come over here, please. Sorry about this. I'm just trying to make this easy to see as I go through the algorithm. And I apologize that I just require additional setup. There we go. Close this. Move. We don't need this anymore. Don't save. Okay. I move forward with Pontifex. Then OBS should move over here. Right. Okay. There we go. And now, full screen projector preview. Boom. On projector 2. Great. Which means now if I do this. Haha. Success. Sorry. Technomancy at work. Right. All right. So the first thing we need to do, so let's go through these 5 steps. The first thing we do is we find the first Joker. Joker A. Not the first one, but like Joker A. Because the first one would be you've got technically that's positional. So we find Joker A, I had him between 8 and 9. Right? And what we do is we move him 1 card down. So he was between 8 and 9, now he's going to be between 9 and 10. Okay? Next one is Joker B. I find Joker B, and I move the Joker B 2 down. That makes sense to everybody? For step 1, take Joker A, move it 1 down.
Where did you have Joker B?
I had it between the 6 and 7.
Of the black cards?
Yeah, of the black cards. All right? Okay, so move Joker A down 1, move Joker B down 2, and now step 3 is where it gets interesting. It's what we call the triple cut. So we take all the cards above the first Joker, okay, and I'm gonna do it like I would do, like I'll write this algorithm. I'm gonna take all these cards, I'm just gonna set them aside. All the cards above the first Joker, then all the cards, basically all the cards sandwiched between the other between the 2 Jokers. Okay? And then I'll take all the last cards, the cards that were below the last Joker. Okay? So the triple cut, the way that works is that you move all the cards above the first Joker and swap it with all the cards below the second Joker. First and second being basically the positional. Right? So here I'll take the ones that are... So now I took the cards that were all, the 8s through the 9, and I'll put them below this guy, and I'll take all these guys and put them above. Okay, so I'm starting and I've got 9, 10, Jack, Queen. Okay, and now we do count cutting. Okay, so I remove the bottom card of the deck, get rid of it for a second, and then I count down from the top card by the quantity of cards equal to the value of the bottom. So if it's a Joker, you let that value be 27 no matter what. Okay. So what I'm going to do is that I'm going to cut down from the top guard. So 9 cards. 1, 2, 3, 4, 5. Oh, right. Be sure to keep them in the right order. So, as I was not doing. So 1, 2, 3, 4, 5. 6, 7, 8. And 9 total. Take those group of cards, move it to the bottom of the deck. And now take this card that we had used last, and now move that back on the bottom. Okay? Alright. So now the last step to generate it. So if we go through it, right, what we did was that we moved the Jokers. We shifted each of the Jokers, we did a triple cut, then we did a count cut, right? We looked at the bottom card, took it off, grabbed a bunch of that many cards from the top, moved it to the bottom. Last step, take a look at the top card's value, which for me is a king of hearts. And what we're going to do is that we're going to keep it at the top of the deck. Count down that many cards. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so we don't remove that card. And so now 4 will be the key for the first letter. And then we just simply put it back the way it was. Okay? And we have and we have an example here, right? With the actual numbers. Let 27 and 28 be our jokers. So here's our initial configuration. First thing we do is swap down 27 and 2. So we had 27 and 2, we swap them. Next thing is we move 28 2 places down. 1, 2. Next thing we do is the triple cut. We take everything above the first joker and everything below the second joker, and we swap them. The bottom card is a 6. So we take the first 6 ones, 5, 8, 11, 14, 17, 20, those first 6 numbers, and we put them over here. And then the top card is 23. So thus we get the 24th card. So we grab it. So 23, 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23. And so our 24, so the next card, which would be this one, is the 11. Although easily enough, you can just simply look at the top card and ask yourself to get what's at index 23, right? That's going to be your keystream value. We look at the top card, and that tells us index 23. That's going to be our key stream. There's a self-test in there if you want to make sure you're understanding it, and the answers are right over here at the bottom. So what you're going to want to do is basically write an encryptor and decryptor for this program. Okay, so now you probably haven't dealt with encryption too much. So let's just talk about the easy ways to do this. The easiest way to do this is to model your deck as a circular linked list. And because a lot of times what you're going to be doing is you're going to be looking at the top card of the deck and moving stuff around that way. Or you're going to be looking at a card, looking for a specific card and moving it down one. So linked lists are really good for this kind of manipulation. And you can simply read in a deck of numbers, and you can use that in the file, from a file or a command line, or you can have it in an array. You can have that deck stored internally. You don't have to necessarily type it in every single time. You can have it stored internally. And then ask your user for a message to decrypt. Right? And then it uses this algorithm to decrypt it. Now, how do you do this encryption? Encrypt a key? That's what we've got over here. Now, the thing is that numbers, so how many of you learned about the difference between characters and integers in Java? Right? So, refresher, characters are not integers. They are not. Never have been. And it's, characters are integers. The characters are integers. And Java likes to treat them as they're not sometimes, but honestly they are. So it's based off of, so modern day programming characters is based off of something called Unicode, which basically means that for the longest time, because computers were English language dominated, we didn't really care what the rest of the world thought about strings and stuff. So again, if I were to put in a Japanese character, my hands, would kind of throw up its hands, because we used to just use simply a byte to store a character. A byte holds 256 possible values. Anybody know how many Chinese characters there are? Yes.
A lot more.
A lot more than 256. How many? Several thousand, yeah. I think there's 2,000 official Japanese kanji, which are basically taken from the Chinese glyphs. And that's just the official ones. Unofficially, there's like 24,000 Japanese kanji. That, you know, so yeah, that's not going to fit. So instead, we're going to just, we've come up with a system called Unicode, but the beginning of Unicode is exactly the same as ASCII. So let's go ahead and take a look at car C. Right, C is equal to, let's go ahead and give it the value A. Or actually, I'll give it the value, I'm going to give it the value D. I can actually store it in an integer, or I can find out its integer value quite easily by just saying C plus 0, the number 0, right? So what happens is that if I see a character, it will convert it into an integer, because a character really is just an integer. We're just translating it into a letter. That's what a character is. It's just a number that we're translating into a letter. And what we're doing is that whenever we see the letter D, we are going to be translating that into 100. I'm going to call this letter, by the way, instead, to avoid confusion. So letter plus 0 is going to be equal to 100. So if I want the letter that's a couple after it, a 2 after it, so which is D, with D, E, F, basically what I would have to do is I'd have to take this and I'd have to cast it into a character. Right? So I add 2 to it, I cast it into a character. However, we get into some issues, right? Because of the way this rotational stuff works, the rotational nature of encryption, if I add 28 to this, right, it should, what should it be doing? It should basically be the same letter, right? 28 is equal to 26 plus 2. 26 is equal to a full rotation. But I don't get that. I get this character over here, /200. And the reason is because that's a valid character. I'm getting 100. I'm getting the character for 128. What about 27? Getting that character. What about 25? I'm getting close curly brace, which is not a letter. So what we have to do is actually, if we want to work in that space, we actually have to do something a bit manipulative. The first thing I have to do is that if I want to get the letter 2 after, like 25 or 27 after, what I have to do is I have to subtract A from letter. Why A? Well, I'm working with lowercase letters, and A's value is 97. It is basically the first letter. So basically it gives us our offset. So by subtracting A, I'm now in the space between, what? 0 and 25. If I subtract A from any letter, it's going to end up being between 0 and 25, right? So now, if I do that, and then I add 3 back, and then I add the rotation I want to put to it, 3, I'll want letter 6. Or if I want to say add 28 to it, then I can mod that by 26, and it'll give me that letter. So again, 28 is 2 after, right? So yeah, 2 after D. So now if I say I want to take this So now how do I get it back and turn it back into something the computer will understand? I add A back in. And then convert it into a car. Holy parentheses, man. It's like it's Lisp or something. Okay. So I've broken that stuff out into steps over here because that's much easier. The way we encrypt a character in some plain text to key is that we convert the letter to a number by subtracting A from it. And then what do is that we figure out how much we want to rotate it forward. We call that value the key. So we add the key and mod 26 to it. And then to get it back into the letter, we add A back to it. Does that make sense to everybody? So you subtract A to get it between 0 and 25, right? That way, and then that way it will work with doing mod 26. If we didn't do that, it would kind of all go to hell in a handbasket. Okay. Then so once we subtract A, we mod it by 20. The parentheses are actually very important here, because if you did that, if we did the modulo first, that would take precedence. So if we without the parentheses, modulo would happen first. It would take precedence over the plus, and so you'd be doing key mod 26 plus letter to num, and that would not be what you wanted. So here we take the key, add it to letter to num, and then this will basically rotate it the appropriate number of steps forward, and then we add A back in. So we subtracted A to get it from 0 to 26, and then we would add A back in to get it from the 97 to 97 to 123 range. To decrypt a character, it's kind of similar. We subtract A and we add A back in as the last steps, right? So the last steps are exactly the same. The middle step is slightly different, right? When we added a character, what were we doing? Sorry, when we were encrypting, we were adding a rotation in, right? We were saying move forward. When we were decrypting, we are subtracting that key instead and moving backwards. However, when we do modulo, if we have a negative number and mod it, that number will still be negative. So what we have to do is that if this result is negative, then we add 26 back in to make it positive. Right? So if for some reason basically that we need, so like say we were moving A, okay, say we were given A and we wanted, and the key was 1. So 1 before A is Z. So if we did that, we would have 0, we'd have cipher num, that would be 0, minus key, which would be 1, so we'd get negative 1 mod 26 would be 26, which is too much. So instead, if decrypted number, sorry, that's too little. It's a negative number, that won't work. We don't have a negative alphabet. So since negative 1 is less than 0, we'll add 26 to it, which will give us 25. Negative 1 plus 26 is equal to 25. And there we've got our key. So this is this is how you would encrypt and decrypt. I'm giving this to you because it's a pain in the butt, and time is limited, and I care more about you getting the linked list stuff down, right? So let's talk about the linked list implementation to do, which is the bulk of the program. Basically, it's split up into three parts: linked list implementation, encryption algorithm implementation, and the encryption implementation, which I just gave to you. Okay, so you've got the linked list portion of it. You basically have to program in the add and remove functions. That's really all you have to do. Add and remove, and you'll probably want to add a get and set. You'll probably also need the get node, but the get node will also work. The get node I gave you in my code will work. Yes?
Actually, I'll let you. It's related to it.
So the add function and the remove function, they have 5 cases. They're identical to the 5 cases you have in a doubly linked list, but you're only going to be using a single link, right? But those 5 cases are the same for add and remove. So you just have to implement the 5 cases. And the biggest difference is whenever you modify the head or tail, you got to make sure that the head points to the tail. Sorry, the tail points to the head because it's circular linked list. Yes.
So, in the circular linked list class, you want us to for the get node, you want another exception in there as well as because it said that
you won't need to.
Well, because here's my question is that I added a condition that like if it's larger than the size it'll keep looping, but then it also checks for the add and remove if it's in the index. So like if you're trying to get something and the number's larger, it'll actually loop around.
You can modify it however you want. Yeah, I'm a big fan of if it works, it works.
Do we have like an important package?
You shouldn't have to. So this I'll say is due by Saturday, right? I'll see where everybody is, but I suspect this is to this week's homework essentially. This one isn't. This one is basically again basically the biggest project I have. So, and we'll be focusing on it all of today, essentially. And it took me like 45 minutes to explain all the concepts, so you know. But I wanted to give you guys a thorough understanding.